The next one is number 16. Here 3 integers are given and their prime factorizations are also given. We have to verify, we have to confirm that each one of them is an absolute pseudo-prime. So here we can use theorem 5.3, the last result of this section, with this observation. Note that this is a product of distinct primes. Which is one of the conditions that we need in that theorem, that the number has to be square free. That is, it should not be divisible by the square of any prime. That's the case here. Also, when we subtract 1 from each of these primes and get the numbers, for example 4, that divides this minus 1. That is, 4 divides 1104. Similarly, 12 divides 1104 and 16 also divides 1104. You just have to verify that these divisibility relations are true. So all the hypotheses that we need in theorem 5.3 are now available to us in this case. So by theorem 5.3, this is an absolute pseudo-prime. Parts B and C are exactly similar, so they are left to you. Okay, so you do these two. Let us next see number 18. And the odd numbered exercises you will have to try yourself. From now on, we won't touch odd numbered exercises. And also, I won't really solve each and every even numbered one. There also, whenever I see that some exercises are similar, I will just do one of them. Otherwise, it's just taking too long. This one has 2 parts. When n equals 2p, where p is an odd prime, prove that a to the power n minus 1 is congruent to a modulo n for any integer a. Now, before we see part B, let us solve this one. Okay, so see, n is the product of 2 and p, and because p is odd, so p and 2 are relatively prime. So at one time we are going to consider one of these things. That is, say first we will consider the modulus 2 and then we will consider the modulus p and then we will combine them. You already know how. So let us first consider 2. Since, okay, so in the beginning, not like this. In the beginning, we clearly say that a is any integer. Since this and a are either both even or both odd, and this of course depends on the evenness or oddness of a. If a is even, then so is this power, and if a is odd, then that power is also odd. So that is why this is congruent to a modulo 2. But why? Well, say a is even, then this side is divisible by 2 and this power is also divisible by 2. So obviously their difference is also divisible by 2, that is the difference is even, and that is why they are congruent to each other modulo 2. But if a is odd, then this is odd, this is also odd. So their difference is again even, and that is why that is again divisible by 2. That's why we have this congruence. Now we concentrate on this modulus p, and here there will be two cases depending on whether p divides a or p does not divide a. Since a is any integer, any one of these two cases may be true. If p divides a, then clearly we have this congruence, but now the modulus is p, because now both sides will be congruent to 0 modulo p, because p divides a. So now we consider the other case. Suppose p does not divide a. Okay. So in that case, what we can do, then by Fermat's theorem, yes, I mean we will have to use Fermat's theorem, but we cannot just write one congruence and the job will be over. There is something. Should I write like, no, hold on. The way I am writing it here, it seems like the Fermat's theorem is going to give us, because of this non-divisibility. No, that's not exactly it. The language is a little confusing. Yeah, let me first say something here itself. Then P and A are relatively prime. Yes, this makes sense. So that is one thing. Now separately, Alright, now let us concentrate on the nth power of A. Okay, this is congruent to, so you write what n is 2p. Okay, now this of course is just this, and at this step we are going to use Fermat's theorem. Fermat's theorem tells us that a to the power p is congruent to a modulo p, and that's why we can replace a to the power p with a. So this will become a square. Let me write mod p here. Okay, so at this step we are using Fermat's theorem. Now we can cancel 1a from both sides. Why? I mean, what gives us the liberty of doing so? This fact that a and p are relatively prime. Otherwise, we cannot just simply cancel it. So you write since a and p are relatively prime, so after cancellation we have this. So you see that besides this congruence is also true regardless of what the case is. Whether p divides a or doesn't divide a, it continues to be true. And now finally you use the fact that p is an odd prime. Since p is odd, so GCD of p and 2 is equal to, you avoid this, the way I have written it here, you please avoid this type of writing. If your sentence kind of stops here, I mean the word part, you write it here, not like this. Okay, you write the entire thing here, GCD of p comma 2 equal to 1 in a separate line, and then you continue. Hence, we can combine these two congruences and have this. I.e., that's what we wanted to establish. So that is part A. Now next let us see part B. For n equal to 195, which is 3 times 5 times 13, verify that the n minus 2th power of A is congruent to A modulo n. For any integer a. So this is also a number whose factorization is given, and here also we have only primes. Only primes means it's also a square free number. It's not divisible by the square of any prime. Alright. So what we are going to do here, also we will start with any integer a and immediately apply Fermat's theorem to a separately for these three primes. That means we are going to have the solution like this. The solution will begin like this. Let a be any integer. By Fermat's theorem, we are now going to have three congruences. A cube is congruent to a modulo 3. A to the power 5 is congruent to a modulo 5, and that one is 13. Mod 13. Okay. $195. So that means we have to now look at the power a to the power 193, 195 minus 2. If we do things slowly, it will take some time. But I have a calculation here. It is a little faster, hence. But whatever I do here, you please verify all the things yourself, especially the parts which are numerical, because we make mistakes. No? So you should not take down the mistake blindly. So this is what we get. See, first of all, this power can be broken down like this. A to the power 3 to the power 4 square times a to the power 3 cube times a cube times a. You may have guessed why we are concentrating or why we are trying to find powers of 3 in the exponent itself. See, the thing here, the logic here is this. Now what shall I do? I am going to replace a cube by a, because here there are 4 3's. So what does this mean? A cube, whole cube, whole cube, whole cube. So every time you replace a cube by a, you get another a cube. Say I replace, let me show it here to make it even more clear. So this is what we have. So first, when I replace this innermost a cube by a, I get this. So this is again a cube. That I will replace again by a. So I am left with another a cube. That will also be replaced by a, and finally this cube will also be replaced by a. This means that this 81th power, 3 to the power 4 is 81, 81th power of a ultimately is congruent to a modulo 3. So I can simply write a here, a square it will be. Now the thing you have to verify to make sure that the calculation is true here is that 193 really is 2 times 3 to the power 4 plus 3 cube plus 3 plus 1. You see that it's true. If not, you inform me. So this ultimately becomes a square. Similarly, here there are three exponents. So ultimately this one will give us a, and this anyway is to be replaced by a and then finally a. Now what are we getting? You see, what do we have here? These three a's are giving me a cube again. So that a cube will be replaced by a. That means again we are having a cube. So this is congruent to a. I can write a little more carefully and write the modulus here itself. Okay, so a to the power 193 really is congruent to a modulo 3. Similarly, we are going to go for the other two primes, 5 and 13. And accordingly, the way we break this thing down now will be different. For 5, it can be broken down like this: a to the power 5 cube times a to the power 5 square whole cube times a to the power 5 whole cube. You have to be very careful with these things, okay? This is that power of a where the exponent itself is 125. However, this is the cube of a to the power 5. So really it is a to the power 15, whereas this one is a to the power 125. These are two different things. And there is one more factor, which is a cube. Okay. Now our modulus is 5, so do not write a in place of a cube, okay, it's no longer 3. So that same logic you can apply here. So this will ultimately turn into a. This one will become a, the inner thing will become a, and already we have a 3 exponent. Similarly, here also a cube times a cube. Alright. So what are we getting from all these things? Nine. Alright. So 9 means 9 plus 1, 10. Have I done some kind of mistake? That's what I am thinking. 5 square. Oh, see, yeah, yes. Yeah, that's why it's not coming. This is 2, not 3. So now if I combine this a and a cube, I get a to the power 4. And these middle terms give me a to the power 5. I cannot do anything with a to the power 4, so let me just keep it as it is. But this I can replace by a. But these two things again give me a to the power 5. So this is congruent to a modulo 5. Yes. And finally, we go for the prime 13. And here, this is how it has to be broken down. 13 square, which is 169, times a to the power 13 times a to the power 11. So, using this congruence repeatedly, this one becomes a, this one also becomes a, this one is a to the power 11. So, 11, 12, 13, which is again congruent to a modulo 13. Okay, so now we are going to combine these three congruences using the fact that these moduli are pairwise relatively prime. So, we write since three, 5 and 13 are pairwise relatively prime. So, a to the power 193 is congruent to a modulo their product, which of course is our n, that means 195. So, that way, using Fermat's theorem, we have proved this, and this is true for any integer a. Next, let us see 20, and with this the section itself will be over. Show that (561) divides 2 to the power 561 minus 2, and that same number also divides 3 to the power 561 minus 3. There is an information which comes with this exercise. The author says that it's an unanswered question whether there exist infinitely many composite numbers n for which n simultaneously divides 2 to the power n minus 2 and 3 to the power n minus 3. Are there infinitely many such composite integers n? That is unknown. And the solution here is quite easy, fortunately. Easy because you are able to use theorem 5.3 here. So, more than actually I should not write solution, but this is a hint. Use theorem 5.3 to show that 561 is an absolute pseudoprime. So, if you show that thing, what will happen? A to the power 561 will be congruent to a modulo 561 for any integer a. In other words, 561 will divide a to the power 561 minus a, and then in place of a you can take 2 and 3. So, there also these divisibility relations will be true. So, automatically these two things will come out as consequences. So that way you can do this. And that just concludes this set of exercises. And the next section is Wilson's theorem that we will start next week. So let me just end this video here itself. So today we did number theory. So that means tomorrow we are going to do what? Oh, tomorrow, okay. Tomorrow we will start complex numbers. I think I got a little confused with this schedule. I slightly changed it recently. So I will have to see. We will see what it is, or maybe you already know better than me. So see you tomorrow with whatever it is. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.